Hi, everyone, and welcome to the Textiles Sorting Using Intuitive Hyperspectral Scanning webinar. My name is Marissa DuPont. I am the marketing specialist, and I'll be your host today. Just a few FAQs before we begin. Apparently that's hard to say. This webinar is being recorded and should be available for viewing within 48 hours. We will answer as many of your questions live as possible during the Q&A session. And additional questions can be answered by email after the conclusion. Just email marketing@headwallphotonics.com. Our agenda will start with an introduction to Headwall, related products, what hyperspectral machine vision is, our feasibility study, and then our Q&A and wrap up. You can ask questions using the questions panel in your GoToWebinar control panel on your PC or your phone. And here are a couple of screenshots that show where those are located. All right, I'd like to introduce our panelists. Will Rock, Ph.D., who is our product manager of machine vision here at Headwall, and George Killian, our application scientist here at Headwall. Will, take it away.
Thank you very much, Marissa. So I'm going to start off today's webinar with a brief introduction to Headwall Photonics. Headwall started off as an optics manufacturing company specializing in holographic gratings, but was founded as Headwall Photonics in 2003, and recently in 2022 was acquired by Arsenal Capital Partners. So since we have been acquired by Arsenal Capital Partners, Headwall has made some additional acquisitions, including holographics out of Marlborough, Massachusetts, perClass out of the Netherlands, and Innospec out of Germany. And we're very excited about all of the additional capabilities that these great companies add to the Headwall group of companies. So now Headwall is greater than 1,000 skilled employees worldwide, and we offer or did I say 1,000? I meant greater than 100 skilled employees worldwide. We're not quite that big. And Headwall is a vertically integrated company offering the total solution from manufacturing the optical components that go within our sensors, design solutions, manufacturing imaging spectrometers, the software solutions that allow you to get the most out of your instruments, and then support for the instruments as well. And Headwall has about 40,000 square feet of engineering and manufacturing facilities worldwide. Next slide, please. Headwall is divided into three main business areas: machine vision, remote sensing, and OEM optical components and assemblies. Today's webinar is going to be concentrating on the machine vision sector of the business, as we're talking about a textile sorting application. But just to give you some brief notes on the other areas of the business, in case you're interested, the remote sensing sector concentrates on airborne deployments of our imaging spectrometers, mainly on drones. We offer turnkey UAV solutions that allow you to put the drone in the air and very quickly and intuitively start collecting hyperspectral data. And the OEM optical components and assemblies, Headwall offers a variety of diffraction gratings, waveguides, and micro lens arrays. So please, if you're interested in either of those, visit our website to learn more information. Next slide, please. So now I'm going to give a brief overview of our machine vision products. First, I'm going to highlight our three flagship machine vision products. First, on the far left is the MV.C NIR, which is the smallest and lightest imaging spectrometer in its class. You can see because of the photo of the hand in there that it's about the size of a deck of cards and offers a spectral range of 400 to 1,000 nanometers and USB 3.1 connectivity. The middle sensor is Headwall's MV.C NIR sensor, which is a new offering giving a spectral range of 900 to 1,700 nanometers and designed specifically for machine vision. The MV.C NIR can offer greater than 500 hertz of frame rate at the full spatial spectral frame, and even faster frame rates than that if you limit the spectral axis. And finally, on the far right is Headwall's MV.X, which is a machine vision hyperspectral imaging system. So the MV.X comes with ingress protection and onboard computing, allowing you to acquire the data and deploy analysis models all in one box, and then output the actionable information at the end. So please, on the next slide. I'd also like to highlight the new perClass Mira stage and software. So the perClass Mira stage offers an intuitive way to acquire and hyperspectral data, and it is really a new, very nice stage package that supports all of Headwall sensors and can be purchased along with an MV scan package, which I'll talk about on the next slide. The MV scan package includes the perClass Mira stage, and it comes with an optional computer, lens, and the sensor to give you everything that you need to collect, train, and deploy hyperspectral solutions all in one box. And so we really like to emphasize, especially on the next slide, the ability of these MV scan packages to offer an intuitive solution to enable you to collect data. So out of the box is everything that you need to gather hyperspectral imaging data, and then that data will be instantly available within the perClass Mira interface, allowing you to train pixel classifiers, and then beyond that, create object segmentation models and even regression models, all within the same acquisition interface. And perClass Mira even has features and functions available to users that want to extract certain information, like say average spectra from different objects in your data set, or even to create index images to give you images of enhanced contrast using the hyperspectral data. And finally, also within the perClass interface is the ability to deploy these models that you've just trained. So there's also a recent addition to the perClass Mira software is the operator interface, which once you've trained the model, this gives you a simplified interface to allow a technician to deploy the model and get graphical statistical results and information about the model as data is being collected or as scans are going by. And so we're very excited about all the possibilities opened up in the MV scan packages. And one final feature that I'd like to note about the perClass Mira stage is that it all fits into a nice Pelican case, enabling you to easily transport it from place to place, and it can even be checked as luggage on airline flights as well, where I have personally utilized that to take it to trade shows to demo to people. Or if you're really interested in the product, please contact Headwall and we could bring one to you to demonstrate the powerful capabilities of this package. And so finally, I'd just like to highlight the more of Headwall's hyperspectral imaging machine vision offerings. So you can see on this slide the three sensors that I previously highlighted: the MV.C NIR, the MV.X, and the MV.C NIR. In addition, you can see the NIR E series, which is the scientific grade sensor, offering thermoelectric cooling, and so a little bit better noise performance, and the SWIR sensor, which is based off of an MCT array, giving a spectral range all the way from 900 to 2500 nanometers. And finally, on the far right, we are highlighting Headwall's NIR packages. So another recent addition to perClass Mira with the release of perClass Mira 5.0 is the ability to scan with multiple sensors simultaneously. This would allow users to purchase the Headwall NIR MV scan package. So with one push of a button, you can acquire a NIR data set and a NIR data set, allowing you to rapidly prototype different solutions and figure out what spectral range and what sensor is the most appropriate for that particular solution. So now that I've given a brief introduction to our product portfolio, I'd just like to highlight that there's additional online content available, so please visit our website. You can see video demos, previous webinars, other tutorials, and you can also view use other handy tools such as the field of view calculator to get an idea of how to deploy these sensors. And you can also browse our website to learn more about the Headwall group of companies, including perClass, Holographics, and InnoSpec. And so now I'd finally like to offer a brief introduction to hyperspectral imaging for those of you that aren't intimately familiar with this technique, so you're able to follow along more cleanly when George then takes over and talks about the application of interest. So hyperspectral imaging is the combination of imaging and spectroscopy. As you can see in this slide here, we've depicted hyperspectral imaging as being hundreds of different color channels in one image. So if you like to think of imaging as your standard RGB image, that would give you 3 color channels, red, green, and blue, where a hyperspectral image can give you hundreds of color channels, again, as you can see in that cartoon on the right. You can also think of hyperspectral imaging as having a full continuous spectrum at every spatial pixel in the scene. So I like to think of it as hundreds or even 1,000 spectrometers in one box. And this will allows you to deploy the tools of a spectroscopist, where at every pixel in the scene, you can compare your spectrum to a model to identify that chemical content at every pixel in your scene. So a better illustration of that is shown on the next slide, where we are showing an image of 6 different white powders. And so to the naked eye or to an RGB image, these all look like white powders, so they're difficult to differentiate. But as you can see in the spectral content shown on the sides of these, that in the near infrared, these white powders have very distinctly different spectral shapes. And so when you take a hyperspectral image, you can create a library that recognizes each of those distinct spectral shapes. And when a scan is taken, the scan pixels will be compared to your library spectra. And whenever you have a good match at a certain spatial pixel to a spectrum in your library, that pixel will be recognized as that material. And you will build up, for visual purposes, an image like you can see on the far right, which is a false color image, where, for example, the upper left powder is sodium chloride. And so every spatial pixel that has a spectrum similar to sodium chloride will be colored that light blue. Every spatial pixel that has a similar spectrum to the, I believe it's sodium bicarbonate in the upper right, will be colored green, and so on and so forth for all of the pixels in the image, as you can see on the far right. And again, it's a nice example of how to create a pixel classifier. And perClass Mira even offers more features and functions beyond that. Once you have a pixel classifier, you can identify contiguous areas of classified pixels as objects. And then once you have objects, you can even train regression models to tell you about different regression targets in that object, as George will talk about in a little more detail later in the webinar. So finally, all of Headwall's imaging spectrometers are push broom imaging spectrometers, meaning that they're line scanners. And so this slide shows a cartoon of acquiring line scan data. So line scan data means every time an image is snapped, we're only getting a line or a sliver of the scene. So that requires motion in order to build up an image. And so this lends itself very naturally to something like a conveyor belt, because a conveyor is always moving along. You can use that natural conveyor belt motion to build up an image of your scene. And as the conveyor moves under the sensor, you're gathering image after image and building up a scene. And on the, which is depicted in the middle image, and on the far right, we're showing, again, another example of the false color image. So as we're gathering every frame, that model that was built is identifying the spectrum at every spatial pixel as it's going by, and identifying that spectral content in every spatial pixel and producing that classified pixel classifier image. And then if you've trained an object segmentation to recognize objects, as an object is fully passed under the sensor, the software will say, okay, I found an object, and then it can tell you where that object is, what material that object is, and if you've built a regression model, it can even tell you the regression value of that object. And so this is all very powerful functionality that is available for runtime deployment using perClass Mira. So with that introduction, I'd like to start the meat of the feasibility study and hand it over to George for him to talk about some recent work that we did demonstrating the ability to sort textiles using hyperspectral imaging.
Thanks, Will. So here at Headwall, we like to solve problems. And so what's the problem when it comes to recycling textiles? Well, one is that there's lots of textiles that desperately need to be recycled and repurposed. The EPA estimates that only 15% of our 25 billion pounds of post-consumer textiles are actually recycled, while the remaining 85% ends up in landfills. The challenge, however, with recycling textiles is differentiating between similar looking fabric at a high throughput. On the next slide, you'll see that there's lots of different methods that are used today in order to be able to sort textiles. For example, chemical sorting, which requires destruction of the fabric and is unable for some similar textiles. While other imaging solutions are out there, such as RGB or multispectral, these can sometimes fail to sort adequately between different textures, especially textures that have very similar chemical signatures. The ideal solution that we would love to have for our ability to recycle and repurpose more textiles would offer a non-contact solution, so as to remove the need for chemical sorting, and can sort blends at high speeds that are similar or even blends of multiple different materials. As we know, if we look through our closet, not every piece of fabric that we own is one single material, but oftentimes blended together in many different ways. On the next slide, we can see the chemical signature of some common textiles and why our traditional sorting methods may not necessarily be able to function. If we were to look at the textiles on the left-hand side, we see that their chemical signatures are very similar. And if we had to pick only a few of those spectral bands to try to sort between them, we might run into some difficulty. However, with hyperspectral imaging, when we're gathering the entire spectral range throughout the entire near infrared range, we might be able to distinguish between those textiles better than before. And that was the goal of this project. On the next slide, our feasibility study, our objective was to be able to determine if we create sequential models that could sort between pure and blended fabrics. The idea being a primary classification model would be used to sort between different fabric types coming in, determining which of the major fabric types was present in that fabric swatch. Then a secondary regression model would be used to estimate the percentage of the blend of fabric. This would resolve the problem where a primary classification model could sort between similar fabrics, and then the secondary regression model will be able to estimate the percentage of fabrics for blends. And this would allow for full non-contact screening of fabrics while resolving all of those issues I just mentioned. For our methodology, we used our perClass Mira software, perClass Mira stage, and our Headwall MV.C NIR Hyperspectral Imager, which gathers data from 900 to 1700 nanometers. The different types of fabrics that we used were acrylic, cotton, linen, nylon, polyester, viscose wool, some cotton blends, and some polyester blends. The perClass Mira software, for those that are not as familiar with it, I'll go into a little bit more detail than Will mentioned earlier. It was used for our acquisition, analysis, and deployment. Classification, regression, and index visualization models can all be created via the simplified user interface. You don't need to be an expert in hyperspectral imaging to take advantage of all the great abilities within hyperspectral imaging for sorting. And as mentioned earlier, these models can be deployed in real time. For a classification model to be built within perClass Mira, we first image the different swatches of fabric on our perClass Mira stage. Then within perClass Mira, we select pixels of each of the different fabric types and add them to a particular class. So for an image of cotton, we take a small sampling of pixels from an image of cotton fabric and build up a cotton class that creates a mean spectra for that particular class. And perClass Mira can sort between many, many different types of classes to be able to sort on a per pixel basis. The model that we built was built and tested against test images of similarly colored and different types of fabrics. On the next slide, you can kind of see how this workflow goes about. First, we take an image of different types of fabrics. Then we're going to paint the pixels and select those pixels and add them to the class. In the middle slide, once a classification model has been built, perClass Mira will assign a class for each pixel in that scene. If you look closely, you can see that the two fabric types that we've chosen for this particular image are acrylic, shown in green, and nylon, shown in pink. They have similar chemical signatures, as we can see from the reflectance plot on the right, and we can even see that on a per pixel basis in the middle, we see that some of those nylon and acrylic pixels are being misclassified. However, within perClass Mira, we can also do object segmentation and classification, where perClass Mira will identify contiguous regions of pixels of nylon and acrylic, and then make a decision based on that object on how many of those pixels are assigned to each class. For all of those 8 swatches, they were correctly classified, and they are done so because the majority of pixels in each of those objects correctly matches the fabric type. So that's the first part of the problem. Can we sort between different types of fabrics that have similar chemical signatures? The answer is yes. However, what do we do when we have fabrics that are made up of multiple different types of fabric blends together? Well, these fabrics could be threaded together or large pieces could be woven together. So with perClass Mira, what we can do is once we have object segmentation, we can assign a value to those objects and be able to comprise a regression model based off of that. For this particular regression model, what we did was we assigned the percent content of a particular fabric blend to each fabric object that it saw, and then built a regression model so that it could estimate what the percentage would be for test images of fabric swatches. On the next slide, you can see an example of how this model was built. On the top image to the left is an image of a cotton blend. In the middle, we have the classified image. It correctly identified all of the fabric swatches and has built a fabric object. And then we can assign a value to that object. In this particular instance, this cotton blend is 47% cotton. And then perClass Mira will build a regression model and can estimate that percent cotton for training and test images as well. As you can see in the bottom left image, the regression model that was built for cotton blends estimated it to be around 47% as well. And if we look to the graph in the middle there, we see that the regression for the training model that was used for all of the different swatches of cotton, ranging from about 40% to 100%, have very strong correlation. And we further stressed this model by using cross-validation testing to ensure that it would be able to work on a wide variety of different cotton fabrics. If we could try going to the next slide, please. We seem to be having some technical difficulties, so please stick with us as we try to resolve them to go over the final few bits of our presentation.
I think at this point we can just go on because you had actually completed the all of the content that we had on the sorting of textiles, and the remaining of the bit of the webinar was going to be us highlighting some of our events coming up, which included a trip to the ASTA SPICE event coming up. That's, oh, there we go. And we have, I believe we're showing our website here, where you can see the American Spice Trade Association annual meeting that's going to come up in the near future, where we will be. So if you're interested in some spice and adulterated spice applications, please visit that. We also have a webinar coming out on that.
In March, we'll also be covering the hyperspectral imaging used to sort spices and detect adulterants in herbs and spices as well. That concludes our presentation so far when it comes to using hyperspectral imaging as a way of sorting between different textiles and textile blends. At this time, if you have any questions, please add them into the questions chat now, and we'll be working through them.
Okay, I see a question that's come through at the bottom here that says, does the false color image represent the percent blend, or does it only become available in the regression model?
That's a great question. So the false color imaging can be applied for a classification model, or it can be used for a regression model. The false color image that you saw in the middle was a classification where the initial classifier that's built for a regression model correctly identified that there was a fabric swatch there. The false color image that you see in the bottom left, that sort of yellow and purple heat map, showed you an estimation of each pixel within that object on that regression model. But it also reports an entire regression value for the mean spectra of that entire object as well. So does the false color image represent the percent blend, or does it only become available when there's regression? The answer is, if you want to see a regression false color image, you need to build a regression model, but a false color image can be presented for a classification model as well.
And I can follow on a little bit more on that as well. So if you had a woven fabric where you had one type of fabric woven into another type of fabric, in order for your pixel classifier to be able to represent the percentage of each type of fabric, you would need to be able to resolve that weave. And so you would need to have very, very high spatial resolution on your imaging system. And that wouldn't in general lend itself to high throughput screening. And so that's why we decided to deploy regression modeling, where instead of being able to resolve tiny threads in a weave, you zoom out a little bit and you get an average spectrum that it includes some of weave 1 and some of weave 2, the percentage of which can be figured out using a regression model.
This next question is, can you separate polyamide and viscose? So polyamide fabric was not used in this particular modeling, but polyester was. We saw, as one might expect, some confusion in our classification originally, but with some further training of our classification model, we were able to resolve a vast majority of the percentage of the time between polyester fabric, and viscose fabric. This will conclude our time together. If you have any other questions, please do not hesitate to reach out to us via email, and we'll eagerly respond to them as soon as we are able. I'd like to thank our team and Will Rock for this wonderful presentation, and thank you all for joining. Have a wonderful day.